Okay, welcome to the first family edition of Notes with Van Moore. This is Miss Van Moore, and
This is Annika. And this is Mia.
And this is enthalpy of formation and bond energy. So these are the last two ways that you can figure out what the delta H of a reaction is. And this is in your book at
17.4.
And
page number 226.
Okay, so the first way is using standard heats of formation to calculate delta H. And I like this way better than bond energy. It's more exact, and it just makes a lot more sense to me. So you can decide which one you like better. So this is for reactions occurring under standard conditions. And that's 1 atmosphere for
gas
and 1 atmosphere and 25 degrees Celsius for a
liquid.
And heats of formation, and that's kind of this funky, here, we'll get a pen going here. This funky symbol here where we have delta H, and then this weird circle, that's, it has to do with standard. So these are standard heats of formation. Don't worry about what unstandard ones are. And then the F is for formation. And so heats of formation are based on 1 mole of the compound. And there's a table with heats of formation found on page
530
in your book. And so you're going to need your book for the example problems. And one of the things is the, there should be a delta. Oh, no, it's not delta. Sorry, the heat of formation for pure elements in their standard state is 0 kilojoules. So that's like a defined quantity. So basically, it's almost like some books will say like 0 kilojoules is like saying that's sea level. So anything above that requires more energy than pure elements to form, and anything below that requires less energy, or I'm sorry, gives off energy to form. So 0, think of that as a baseline, and that's for pure elements. And then the equation we have, which is kind of, it looks scary, but it's not that bad. So then the delta H of reaction, so the change in enthalpy that we've talked about, is, remember, this here means sum. So let me write that out. Sum means adding together. N we know is number of moles, times the heats of formation of the products, minus the sum of the number of moles times the heats of formation of the reactants, which is sort of what we would expect. We're going to do the products minus the reactants, and so if that ends up negative, it's exothermic. If that ends up positive, it's endothermic. So let's use an example.
What is the delta H of the reaction?
So the reaction is 4 NH3 gas plus 5 O2 gas yields 4 NO gas plus 6 H2O gas. So using the chart found on page 530, see if you can figure that out. Now, girls, do you think it's better to look at the answer first and then figure it out, or should you figure it out on your own and then look at the answer? Figure it out on your own. I would agree with you guys. So you should figure this out on your own first. So go ahead and pause the video and figure it out. So the first thing is, this is the equation we talked about. The sum of the number of moles times the heat of formation of the products minus the sum of the number of moles times the heat of formation of the reactants using the chart on page 530. There you go, table on page 530. And so then this is the entire equation. So this 4 moles goes, oh, let's get that pen back.
4 mole times 90.37.
So where Mia is getting that is, what happened to my, oh, there it is. So this 4 mole goes with that, because remember, it's reactants, or it's products minus reactants. And then the heat of formation for NO, nitrogen monoxide, is 90.37 kilojoules per mole, plus
6 mole times minus 241.8.
So For water, the heat of formation is negative. That means when water forms, it's releasing energy. It's below zero. So that 6 moles is from there, and then negative 241.8 again is from the table on page 530, minus
4 mole times minus 46.8.
kilojoules per mole, plus
5 mole times 0.
5 mole times 0. So remember, elements, and you can see this on the table, but elements in their standard state are just 0. And so, Ani, do you know this one? Do you know what 5 times 0 is?
Zero.
0, that's right. So anything times 0 obviously is 0, so you don't have to count that in your calculation. And so go ahead and calculate that, and make sure you can calculate this with all the parentheses. And our answer is
Delta H of the reaction equals negative 904.6.
and that's in kilojoules, because if you notice, for example, the moles here are canceled by the moles there, leaving you kilojoules, and that happens all along. Okay, so another way of finding out the delta H is by using bond dissociation energy. And dissociate means to break apart. So this is the energy it takes to break apart bonds. One thing to note about using bond dissociation energy is that it's a bit of an estimate. So you're not going to get the exact same numbers, but they should be close to what you get using heats of enthalpy. So, as we said, bond dissociation energy is the average energy to break bonds between two elements. And it's also in kilojoules per mole. The word average here is because, like, let's take water, which is H2O. So water has two bonds that are both OH bonds. But once you put in energy to break this one, it's actually going to take a different amount of energy to break this one, because now you don't have this other bond here. So that's why these are averages. They're not exacts. Bond energies are always positive, because remember, energy is required to break bonds. And so you are absorbing energy, hence a positive H value. The higher the bond energy, the more stable the compound, because the less likely it is to break apart. So the equation is
delta H reaction equals
so the sum of the delta H's of the bonds broken minus the sum of the delta H of the bonds formed. So it's just the opposite of heats of formation, where in heats of formation we did essentially reactants minus products. Here we're doing, in heat of formation we did products minus reactants. Here we're doing reactants minus products, because we're talking about the exact opposite. We're going to start with the sum of the energy to break the bonds, and then we've got the sum of the energy to form the bonds, and we're going to subtract that. So if it takes more energy to form these bonds than to break these bonds, we're going to be exothermic. I also often think about this using this equation.
delta H reaction equals.
So this is the sum of the bonds broken again, but then we're adding the sum of the negative delta H of the bonds formed. It's exactly the same thing, but I find this a little easier that we're adding up all the sums of the bonds, but we're making this negative because we know when we form bonds, the energy is released. So I find this equation conceptually easier, although they are identical equations. So please, if you're having trouble with the concepts, don't try to memorize equations. Make sure you ask in class. It's exactly how it's.
Reaction is exothermic when weak bonds break in strong bonds.
So, yeah, so that makes sense. If we're breaking weak bonds, it's not going to take a lot of energy to do that. And then strong bonds form, that's going to give off a lot of energy when those form because it's the opposite of breaking them. And so that's going to be exothermic because you're going to have a release of heat.
Reaction is exothermic when strong endothermic when strong bonds break and weak bonds form.
Right, so that's the exact opposite. If you have to take a lot of energy to break the bonds, and then not a lot of energy is given off when the new bonds form, that's endothermic. So you can see in both of these, bonds break and bonds form, but it's a difference of energy. Make sense? Mm-hmm. Okay, good. All right. So this is, can you read that?
Bond enthalpy
Good.
table.
This is a bond enthalpy table. There's not one in your book, but this is how much energy it takes to break different bonds. So it's organized by compound, but notice that these are all single bonds and these are all multiple bonds. So for example, it takes, do you have a C? Yeah, here's like a carbon to carbon bond. And so that is 384 kilojoules per mole. A double carbon to carbon bond is 614 kilojoules per mole, and a triple carbon to carbon bond is 839 kilojoules per mole. And so it takes more energy as you go from single to double to triple bonds of the same things. One thing to remember, as I said, is that these are average bond enthalpies, and it says average right here, because it's going to take different amounts of energy depending on how many things you have bonded to the atom. The other thing you need to know is if you're still struggling with molecule shape from way back in semester 1, you may want to go back and review those notes, and I'll post them to the website on this week's blog so you can see those as well. All right, so now let's look at an example.
What is the
Delta
H reaction of the reaction?
Oh, that's right, and we changed that before. This is kind of redundant. We can just say what is the delta H of the reaction. So,
for NH3 gas plus 5O2 gas yields 4NO gas plus 6H2O gas.
so this is the exact same reaction we had before. The trick of this is that the bond enthalpies are, of course, on the previous slide. So you may want to look up bond enthalpies online or take a screenshot of the previous slide and somehow work them. They're not in your book, which kind of sucks. But go ahead and, again, girls, should they figure out the problem first and then look at the answer, or look at the answer first?
Figure it out.
Figure it out first. Exactly. Then look at the answer. Much better learning that way. All right, so go ahead and figure it out. Pause the video. So the equation we're using is, you want to try this?
Delta H reaction equals
The sum of, that means add them together.
the sum of delta H bonds broken minus the sum
The sum means, again, to add them together.
of delta H bonds broken.
And the only thing that you have to remember is when we're looking at bonds broken, you have to take into account how many moles you have. So I actually wanted to leave some space here to draw this in. So like NH3 is NH, H, and this is why it is important to know your compounds and what kind of bonds they form, because if you think, for example, an H is bonded to another H, that's going to throw you off. This is 3 NH bonds, but we have 4 of those. So just remember when you're calculating that it's not 3 NH bonds, it's what's 3 times 4? 12 NH bonds, plus the 5O2 bonds. So again, here you have to understand that O forms a double bond. So that's not an OO bond, it's an O double O bond. And again, there's 5 of them. So what's 5 times 1, Mia?
5.
5. And so those are our bonds formed, or I'm sorry, broken. And then we're going to subtract our bonds formed. So NO is, that one's obviously NO. And there's 4 moles of that. So again, 4 times 1 is, Mia?
4.
4. Plus H2O. And here again, like if you think it's an O attached to an H attached to another H, that's going to throw you off. This is 2 OH bonds. We have 6 moles. Annika, what's 6 times 2? Can you do that? 2 groups of 6?
12.
12, yeah, so we have 12 OH bonds. So that's why it is important to understand how compounds bond. So this would be your overall equation then. We have 4 moles at 3 NH bonds. So each NH bond is 391 kilojoules per mole. There's 3 of those, 1, 2, 3, and it's 4 moles. 4 moles. Plus 5 moles of our O2 bond, which is 146 kilojoules per mole, minus 4 moles, that's 4 moles here, times 201 kilojoules per mole, that's that, plus 6 times 2, here are my 2, 1, 2, at 463 kilojoules per mole. So now go ahead, plug that into your calculator, make sure you understand all the parentheses here. And then your final answer is
Delta H reactions equal negative 938 kilojoules.
good. And again, going back to here, the moles are going to cancel here and here, leaving the kilojoules. Now, if you remember when we did this by the heats of formation, it was like negative 905 kilojoules. So that's slightly off, but that's why bond energy is much more of an average. So it's a good estimate. I mean, clearly, no matter how you calculate it, this is a wildly exothermic reaction. It's giving off a lot of energy. So I do want to do one more thing, and that's I want to run the same equation, but using Hess's law that you already know. So here is the new one. So Mia, you want to go ahead and read this part?
What is the delta H reaction of the reaction?
Oh yeah, and that's right. I guess we forgot that we can take that off. If we're saying of the reaction, we don't need to say that twice.
4NH3 gas plus 5O2 gas yields 4NO gas plus 6H2O gas.
And so this is the same reaction we've been doing, but now we have 3 equations that we can use to put this together. So Mia, you want to do equation number 1?
Yeah.
N2.
N2 gas plus O2 gas yields 290 gas.
And for that equation,
Equals
the delta H equals
180.5 kilojoules.
And equation 2 is
N2 gas plus 3H2 gas yields 2NH3 gas.
and the delta H of that is
Negative 91.8 kilojoules.
And the third reaction is
2H2 gas plus O2 gas yields 2H2O gas. Delta H equals negative 483 kilojoules.
Yeah, and so you can go through and solve this using Hess's law. So again, as I think we've covered, it's better to pause the video, figure it out yourself, and then look at the answer. So go ahead and do that. So the first equation that I used was equation number 2. And I reversed that equation and multiplied it by 2 because I know that I need my NH3 in the reactants, and here it's in the products. And here I've got 2 NH3, and here I've got 4 NH3, so I multiplied it by 2. Then the second equation, or this is actually, the first equation, I left exactly the same, but I multiplied it by 2. Because here I needed 4 NO, and here I have 2 NO. This, by the way, was our warm-up question, I think yesterday, when I didn't give you amounts, but I just, we talked about what you would do with these equations. And then the third equation, I kept going in the same direction, but I multiplied it by 3, because here I have 6 H2O, and here I have 2 H2O, so you need to multiply by 3. These I treated the same way, so I reversed this. This is 91.8 times 2. This one is 180 times 2, approximately. This is negative 483 times 3. And so then I add all these together. This is my final reaction, which is exactly what we have there. And the delta H is negative 905 kilojoules, which is exactly what we got earlier for when we use the heats of reaction, or the heats of formation. And one thing to note is these equations, the way you get these delta H's is using the heats of formation. So you would expect them to be the same, and if you have a heats of formation table, there's no reason to go through. Hess's law actually is an extra step in the process, given that it gives you the same answer. But I did want to show you that that all works out, and hopefully this is helping you put some pieces together. So if you have questions, feel free to put them on YouTube. This is me signing out, and do you want to say goodbye?
Goodbye.
That was Annika, and
Bye.
that's Mia. Have a good night.